Hi, in this video we are going to discuss the ideas of basis and dimension and how they relate to what we term the four fundamental matrix subspaces. This section is going to be quite conceptual, but the concepts are some of the most important ideas in linear algebra. Let's review a little bit about what we already have seen. We've discussed the idea of the row space and how forward elimination gives the dimension of the row space and a basis for it by counting the number of non-zero rows in a row echelon form. We've also discussed the column space and how forward elimination can give the dimension of the column space by counting the number of pivots in a row echelon form. Pivots are, of course, simply the first non-zero entry in a row in an echelon form, which means the number of non-zero rows and the number of pivots has to be equal. This leads us to one of the central concepts in linear algebra. I cannot emphasize too much how important this idea is. The dimension of the row space and the column space of a matrix are the same. The number of pivots, number of non-zero rows. If you recall back to our earlier definition of rank, it's the number of pivots or the number of non-zero rows, this matches this dimension, and this is one of the reasons why we define this idea of rank. It defines the dimension of both the row space and the column space. Okay. Let's now talk a little bit about the parent spaces of these subspaces, the row space and the column space, in the context of an M by N matrix. And we're going to use this notation throughout this section. All matrices will be considered M by N, where M is the number of rows and N is the number of columns. So let's look at the row space first. Well, every row of an M by N matrix, of course, is a vector with N elements, as many elements as there are columns. And this means that the parent space for the row space is an n-dimensional space. We say that the row space of A is a subspace of Rn. This notation here is part of set notation, reads as is a subset of or is a subspace of. There's a similar notation that does not have the line on the bottom that does not allow for the subspace to actually equal the parent space. We need this possibility of equality here because the row space can in some case be the entire n-dimensional space. But no matter how large or small the row space is, no matter its dimension, it will always be a subspace of n-dimensional space, where n is the number of columns. Similarly, each column of an M by N matrix is a vector with m elements, the number of rows, and this means that the parent space for the column space is the m-dimensional space. We say that the column space is a subspace of Rm. What do we mean by a parent space here? Well, just the space that this the row space or the column space sort of lives in. Imagine that the row space was a line, one-dimensional, had a dimension of 1. Well, is it a line in 2D? Is it a line in 3D? Is it a line in 4D? That is the question of the parent space. What is the dimensionality of the parent space? Similarly, if a column space of some matrix is, say, a plane, is it a plane in 2 dimensions, in which case it is all of 2-dimensional space? Is it a plane that lives in 3 dimensions? Or is it a plane that lives in some higher dimensional space? This will be determined by the number of rows. Okay. All right. Now, that was a little bit of a follow-up discussion on the column space and the row space. Now let's return our attention to another vector space we've seen associated with a matrix, the null space of a matrix. Remember, the null space is simply the set of all possible solutions to AX equals 0 to a homogeneous system. And the null space is, of course, a vector space, because if we take any 2 vectors from the null space, their linear combinations also have to be vector of the null space. If I have 2 different solutions to AX equals 0, their linear combinations are also solutions to AX equals 0. We have also seen how we can describe the null space of a matrix by determining a set of special solutions, 1 per free variable. And once we have that set of special solutions, we can define the null space as the set of X that can be written as a linear combination of all of those special solutions. Okay. Well, these special solutions were specifically created to be linearly independent. How did we generate them? We generated them by setting each free variable equal to 1 and all of the rest of them equal to 0 for each special solution. This means that a different free variable is non-zero in each special solution. There's no way then that we can generate other special solutions from one special solution from others, because we have only 0 entries in all of the other free variable positions. By construct, we've come up with a set of linearly independent solutions. The special solutions are also sufficient to describe all of the solutions. The general solution is the set of all linear combinations of the special solutions. Well, if we have a linearly independent spanning set, a linearly independent set that is sufficient to describe the space, that is exactly what we mean by a basis. The special solutions to the null space, which we discussed earlier, are in fact a basis for the null space. The number of special solutions was determined by the number of free variables in an echelon form, and so that is the dimension of the null space. So in fact, we already have all of the tools necessary to determine the basis and dimension of the null space. Okay. Now let's talk a little bit about relationships between some of these spaces. We've already seen how the parent space of the row space is n-dimensional space, where n is the number of columns, because each row is a length n vector, or an n-dimensional vector. We've also seen how the dimension of the row space is the rank, which is the number of pivots. And we've seen how this should not say column space here. This should say null space. the parent space of the null space is also n-dimensional space. Why is this? Well, if we think about the problem of AX equals 0, A is an m by n matrix, means that X has to be a length n vector. X represents the number of variables. There's as many variables as there are columns in the coefficient matrix. Right? That if X for AX equals 0 is a n-dimensional vector, then all solutions to this system must be in Rn. The null space is a subspace of n-dimensional space. The dimension of the null space is the number of free variables. The number of free variables is simply the number of pivots subtracted from the total number of variables, n minus the dimension of the row space, or n minus the rank. All right, and so we see that we have two different subspaces of n-dimensional space, the row space and the null space, and their dimensions are given by the rank and n minus the rank. This second point is really important. The row space and the null space have the same parent space, which is n-dimensional space, Rn. And the sum of the dimensions of the row space and the null spaces equals the dimension of the parent space. The dimension of the row space plus the dimension of the null space equals n, which is the dimension of Rn. Because we have this similarity, this parent space that is shared, and because of the importance of the null space in many problems, we also give a special name to the dimension of the null space. We call this the nullity. The nullity of A is the dimension of the null space. The rank of A is the dimension of the row space and the column space. And this relationship then can be equally written: rank of A plus the nullity of A equals n, the number of columns. Now, why is this such an important idea? Well, first of all, let's note that the null space and the row spaces also have to be linearly independent. How do we know this? Well, for all vectors in the null space, we know that AX has to equal 0. If AX doesn't equal 0, X is not in the null space by definition. Now let's consider, another little typo here. Now let's consider each row, each Ri not equal to 0. Ri here is going to correspond to a row of I, and we're going to limit ourselves to looking at non-zero rows. What would A times Ri be? Well, it would be a matrix where there's some number of rows and one of them is Ri. We would multiply that, and I have the transpose here to highlight that we want a row vector here. We multiply that by the column vector of Ri. And what would this give us? Well, I don't know what it would give us on the other rows above or below, but I know that for this particular entry in the product, it would be multiplying all of the entries of Ri against all of the elements of Ri, adding them together. The sum of the squares of the entries of Ri, which is simply the square of the norm of Ri. That is, the dot product of Ri with itself. Well, we know that the norm is a length, and unless Ri is the 0 vector, a length has to be a positive non-zero number. And so if there's some element in here that is not equal to 0, then this cannot be 0. None of the rows, none of the non-zero rows of A can be in the null space. If the non-zero rows cannot be in the null space, then their linear combinations, or at least their non-zero linear combinations, cannot be in the null space. That is, the only vector that is in both the row space and the null space is the 0 vector. If we ignore the 0 vector, which we already know is in the null space, every other vector in the row space is linearly independent from the null space. Why is this important? This is important because if we take a union of the basis for the null space and a basis for the row space, union just means we take all of the elements and we stick them together. We basically make a bigger basis that's made up of the basis vectors from the null space and the basis vectors of the row space. These will contain n linearly independent vectors. There has to be n of them because the sum of the dimensions of these two spaces is n. They have to be linearly independent because we started with a linearly independent set for the null space, a linearly independent set for the row space, and we've seen that these two groups must be mutually linearly independent. A set of n linearly independent vectors from Rn is a basis for Rn. This idea, this result demonstrates a really, really important relationship between the row and the null spaces. Essentially, the row and the null space together define all of Rn. What we say is that Rn is the direct sum of the row and null spaces. A direct sum of two vector spaces is kind of an extension of the idea of a vector space itself, but using vector spaces to define it rather than vectors. Similar to like the linear span of a set of vectors, a direct sum of a set of vector spaces is the space of all possible linear combinations of vectors from the two spaces. So all of the ways that you can take linear combinations within the row space, within the null space, and between the two of them. The notation we use for this is a plus sign inside a circle. This reads the direct sum of the row space and the null space is Rn. What this means, what this implies, is that every vector in Rn can be expressed as a unique sum of vectors from the null space and the row space. So vectors that are in the row space, of course, are described by a single vector in the row space. Vectors that are in the null space are described by a single vector, by a vector that is in the null space. Vectors that are not in either, so say a vector over here that is not in the null space and not in the row space, can always be represented as a sum of some vector in the row space and some vector in the null space. And this representation is unique. There is only one corresponding vector from the row space and one corresponding vector from the null space. The row space and the null space together give us exactly the amount of information we need to describe any vector in Rn and no more. All right. This idea now actually helps us put in context something that we've seen before, the general solution to a linear system. we've seen how we can write the general solution for some AX equals B in the form shown here, a sum of a particular solution and then linear combinations of the special solutions to the homogeneous system. Okay? We've discussed now how these special solutions are in fact a basis for the null space. And so this set of linear combinations is a vector from the null space. We've seen how every vector in Rn can be expressed as a unique sum of vectors from the null space and the row space. For every vector x in Rn, there is a unique vector in R. This says there exists a unique, the exclamation point here emphasizes not just that there exists such a vector, but that there is a unique one from the row space and a unique vector from the null space, such that x equals the sum of these two. And what this means is that every solution to AX equals B, which of course is a vector from Rn, must have a representation like this. It must have a unique particular solution that is in the row space. When we derived this general result, we said that we can define the set of solutions by any particular solution and the set of all linear combinations from the null space. And that is true. For a general linear system, we can have any particular solution combined with the null space. However, if we want to find, we can define a unique particular solution, which is the one particular solution that lives in the row space. This is actually the solution we get by setting all free variables equal to 0. Remember, all of these special solutions had a single free variable set to something other than 0, set to 1. If we have all of the free variable positions equal 0 in our particular solution, it cannot have any component of the null space in it. So this actually justifies our, gives a framing for why we would want to develop that particular solution. It wasn't only that it was easy to get by looking at the augmented matrix directly, it's also that it has a particular conceptual relevance as the solution that is in the row space. All right. We can also, so if we think about now moving to the column space, right? Can we make any similar discussions about the column space? Remember, the column space lives in m-dimensional space rather than in n-dimensional space. The row space and the null space have this nice relationship that their direct sum gives their shared parent space. So far, the only subspace we've defined of Rm is the column space. In some cases, the column space might be all of Rm, but what about the cases where it's not? Is there an analogous way that we can analogous subspace to the null space that completes Rm along with the column space? The idea that we are going to use to complete this picture is one of a left null space, the null space of A transpose. It has exactly the same definition as the regular null space, just that we're using the transpose instead. If we have some A which is an m by n matrix. The transpose will be an n by m matrix. And we can say, what is the null space of that? And the A transpose has m columns, so the null space of this matrix will be Rm. There are additional relationships between the column space and the row space with the transpose that should be fairly obvious. The column space of a matrix is the row space of its transpose, because when we take the transpose, we change columns to rows. And similarly, the row space of any matrix is the column space of its transpose. So we have a relationship between the column space, the row space of A transpose, the row space and the column space of A transpose. And once we've done this, defined the null space of A transpose, we already know that the column space is the row space of A transpose. We will be able to define something very similar as we just did. We start off with an m by n matrix. We take its transpose. And then consider the row space of A transpose and the null space of A transpose. These are both subspaces of Rm, the number of columns of A transpose. We can sort of draw a picture of this relationship shown here in a very analogous way that we showed before. The row space of A transpose and the null space of A transpose together through a direct sum generate all of Rm. Every vector in Rm can be expressed as a unique sum of vectors from the column space of A, which is the row space of R transpose, and this left null space. There will be some vectors that reside in the column space of A and can be described by a vector only from the column space. There will be some vectors that exist only in the null space of A transpose, in the left null space of A, and those will be described by a vector as such. And there will be other vectors, or there may be other vectors, that are neither in the column space nor in the left null space, but can be described as a sum of one vector from the column space and one from the left null space. And this is a unique representation in exactly the same way we had for the row space and the null space. All right. Let's pause here to consolidate all of the things that we've seen so far. We have a matrix A, it's m by n, that we can always transpose to define a matrix that's m n by m. This matrix has four subspaces associated with it. Four fundamental matrix subspaces. A row space and a null space. These both live in n-dimensional space, the number of columns of A, and together their direct sum gives us all of Rn. Any vector in Rn can be described as some sum of a unique vector from the row space and a unique vector from the null space. These are two of the fundamental vector matrix subspaces. We also have a column space and a left null space that together are both subspaces of Rm, where m is the number of rows. Their direct sum gives us Rm. Every vector in m-dimensional space can be described as a unique sum of a vector from the column space and a vector for the left null space. Okay. We've also discussed now not only what these are, we have the tools in place to find the dimensions of the row space, the null space, the column space, the left null space, and the dimensions and bases for them. All right. That was all a discussion of vector spaces and matrix. Let's now add into this picture the idea of linear systems, which is really what has grounded most of our discussion in the semester so far. Really, for any matrix, we can define two linear systems. Either one using the original matrix, which is the one that we've usually seen, or one using its transpose as the coefficient matrix. So we might write AX equals B, where A is m by n. This means that X has to be an n-dimensional vector, the same as the number of columns of A, and B has to be an m-dimensional vector, same as the rows of A. Right? This is the standard system that we've seen repeatedly. But we could also define a system A transpose Y equals C, where A transpose has, of course, n rows and m columns. Y here will be an element of Rm. I use a different notation here to highlight that these X and Y live in different parent spaces. And the right-hand side lives in Rn. Again, different than the right-hand side of the non-transpose case. Of course, in square matrices, these would all share the same parent space. But in the general case, they may be in different dimensionality parent spaces. Now let's think about how our ideas of the fundamental subspaces can be used to understand these systems. Let's start with the forward system, AX equals B. This is one we've discussed thoroughly already. The column space we have seen is the set of right-hand sides with a solution, the set of possible answers, possible right-hand sides that give us a well-defined solution for AX equals B. The null space is the set of solutions to AX equals 0. We know from our discussion of the role of the row space in how we describe solutions, that for every right-hand side in the column space, if we have a right-hand side that's in the column space, there must be a solution. And there must be a unique solution that is in the row space. And every solution can be written as a sum of that unique solution from the row space and some vector from the null space. So this helps put in, just in the language of row space, null space, column space, and so on, the ideas that we have already seen to hold true. We can add these ideas to this picture of the four subspaces. This is a little bit busy, but let's kind of walk through it fairly slowly. We've already discussed the four matrix subspaces. For the forward system of AX equals B, the ones that are most relevant are the row space, the null space, and the column space. The left null space doesn't play very much of a role. We know that for every system, so what are the kinds of things that we can see in this picture? Well, we know that for every system, AX equals 0 has a solution of 0. And so we can say on the solution side, the vectors x equals 0, is associated with a right-hand side of y equals 0. But ax equals 0 can have more than just one answer. If there's more than one answer, the answers to the solutions to ax equals 0 live in the null space. The null space is the set of vectors that all, when we plug them into ax, we get the answer 0. The column space is the set of all right-hand sides that have a solution. Anything that is in the null space, or anything that has to be written as a sum of a vector from the null space and a vector from the column space, does not have a well-defined solution. Right? For each of these right-hand sides in the column space, there's an answer we can associate it with that's in the row space, a unique answer, a times xr and x equals b. But there is also, if we have a non-trivial null space, a null space of more than just the origin, there are additional solutions for the same right-hand side that can be written as a sum of that same right-hand side, that same solution from the row space, and any solution from the null space. We can think about the set of solutions to ax equals b being found by translating this null space up so that it sits on this solution in the row space. All right. We can take exactly the same sort of analysis for A transpose y equals c, what we might call the backward system, the transpose system. In this case, it's the row space of A, or the column space of A transpose, that gives us the set of right-hand sides with a solution. And it's the left null space that gives us the solutions to A transpose y equals 0. Exactly as we had for the forward system, for every right-hand side that has a solution, that is every right-hand side in the row space of A, the column space of A transpose, there is a unique solution that is in the row space of A transpose, or the column space of A. And every solution for a right-hand side that is in the row space can be written as a unique sum of this unique solution from the column space and a vector from the left null space. We can draw a picture that looks exactly like the one we saw for the forward system, but in reverse. For the system A transpose y equals c, it's the null space of A that isn't particularly relevant. The row space of A that houses the right-hand sides that have solutions. That includes the 0 vector, which always has a solution of 0, but also can have solutions that are the left null space. And for non-zero elements of the row space of A transpose y has a solution, a unique solution that lives in the column space. And if we have a non-trivial left null space, additional solutions that can be written as a sum of a column space vector and a left null space vector. Okay, the last thing I want to do in this video is now revisit ideas of rank and the different possible solution types to a linear system using the additional conceptual understanding, the language of the 4 fundamental matrix subspaces. We'll, in every case, be considering a coefficient matrix with m rows, n columns, and a rank of r. One possible case is that the rank equals the number of rows and the number of columns. This is the case where we have a square, full rank matrix, what we call a non-singular matrix. If the rank, which is the dimension of the row space and the null space, equals n, which equals m, then the column and row space are both the full parent space, and the null space and left null space are both just the origin. In this case, we have a complete null space, complete row space, that is, they're both the full parent space. Every right-hand side has a solution for both AX equals B and A transpose Y equals C. The null space and the left null spaces are just the zero vector, and so that solution is always unique. Another situation we can have is that R equals M. The rank is equal to the number of rows, but the number of rows is less than the number of columns. This is a case where clearly we have more columns than rows, and the matrix is full row rank. In this case, the column space is the full parent space. The column space lives in Rm. It has dimension equal to the rank. If the dimension is m, it's all of the parent space. That means the left null space is just the origin. The row space, however, also has rank m, or has dimension m, but m is less than n. The row space is not the full parent space. The null space is more than just the origin, has dimension defined by n minus r. This means there are many right-hand sides, or many solutions, because we have a non-trivial null space, to every possible right-hand side for AX equals B, because the column space is the full parent space. In A transpose Y, things get turned around. If there is a solution, it will be unique, because the left null space is just the origin, but not all right-hand sides give a solution, because the column space of A transpose, that is the row space of A, is not the full parent space. In the case where the rank is equal to the number of columns, but the number of rows exceeds the number of columns, more rows than columns, but full column rank, in this case it's the row space that is the full parent space. The row space lives in Rn, and the dimension of the row space, the rank, is equal to n. If the row space is the full parent space, the null space has to just be the origin. But the column space, which lives in Rm, but still has dimension n, or dimension r, is not the full parent space. The left null space is not the origin, has dimension m minus r. In this case, AX equals B will have a unique solution if it has one, because the null space is just the origin, but not all right-hand sides give a solution. Flipping around to the transpose linear system, the backwards linear system, there are many solutions to every right-hand side for A transpose Y equals C. The final possibility is that the rank is less than both the number of rows and the number of columns. This doesn't matter whether we have a square matrix or a rectangular matrix, whether we have more rows or more columns. The rank is less than both the number of rows and columns. In this case, neither the row space nor the column space are the full parent spaces. The null space has dimension of n minus r. The left null space has dimension m minus r. Both of them are non-trivial. They include more than just the origin. And for both AX equals B and A transpose Y equals C, not all right-hand sides give a solution, but those that do give many solutions. Okay. This was a very conceptual video. The first video for this unit was more hands-on, more teaching us how we calculate basis and dimension. In the accompanying video, we'll go through some worked examples using the tools that we developed for finding basis and dimension, but to apply them with the concepts that we've discussed in this video. Thank you, and goodbye.